Good morning. It's great to see the room filled. I'd like to, first of all, recognize all the emergency managers and emergency responders here today for your service to New York State citizens, whether it's mitigating or responding to events which threaten our lives and lands. I also want to recognize any veterans who are in the audience for your service to our country, keeping it safe for our families and industries. Thank you very much for your service. I really have three things that I'd like to say this morning. First, the thing I'd like to say is that the university recognizes that we are here to create knowledge by experimentation and observations. It is therefore our responsibility to share that knowledge and our scientists to share our scientists who work in our university with state agencies, with New York State citizens, and with the federal government. Today, we are here to share knowledge and convene important discussions with respect to weather and climate, especially in a world that is seeing significant changes. Second thing I'd like to say is that the university has invested in hiring additional faculty and staff in atmospheric sciences because we understand and we are national leaders in science of weather and how it is changing. We have invested not only because this is a major research strength of the university, but also because it is critically important to carrying out the needed research with respect to prediction and decision making. Events such as this one this morning can provide the evidence-based knowledge and best practices which will aid emergency responders to carry out their mission effectively. This is the value add of a public research university partnering with state agencies. We hope that the new College of Emergency Preparedness and Homeland Security will take this activity to a new level in the very near future and incorporate into these best practices the human condition, the social impact, the social factor, which is becoming more critically important to emergency preparedness and mitigation of personal disaster. So convening discussions such as these today help to really inform the university about what is important to emergency managers and responders, and to learn from others who also serve in knowledge generation as well as service, so that our research can be laser focused on the most important questions that can be translated into practice. Important missions for the University at Albany, translating science and knowledge into practice. The last thing I'd like to say is that the university recognizes the need to be training students to work in high needs jobs. We have a very long history of working with operational forecasting activity, particularly working closely with NOAA and the National Weather Service. These students are highly valued and have unique opportunity of being elbow to elbow with, for example, the Regional Forecast Office headed by our colleague Ray O'Keefe, who will be speaking later today. We also understand the importance of hydrological sciences, and we are delighted to have also our colleague David Valley at the table for these discussions. The university understands the importance of and will be advocating for enhanced research relative to the relationship between atmospheric science and water and hydrology, because of some of the unique New York State geography and the events that are affected by groundwater, snow cover, flooding, and other factors. We believe that by setting the table for these discussions, that we can and will have a collective impact that will be far greater than any one of us can have alone. The impact will be societal, it will be scientific, and it will be operational. So thank you for coming here to listen, but also to have a voice in the conversation. And I particularly want to thank the organizers of this event for consistently good work in making this an annual event. It is now my pleasure to introduce the president of the University at Albany, Jim Steller.
Thank you, folks. My name is Jim Steller. I'm the interim president. It's my 7th week on the job. But I was here 2 years as provost. And one of the things about being provost is I not only get to work with my good friend Jim Diaz, but I got out all over the campus to try to see what was going on through the deans, through the chairs, into the departments and centers and so on. And you just can't help but develop an integrated view. And then what happens when you become president is you want to use that view to try to drive forward the university because you see the connections that other people might not see as clearly. So one of the things I want to recognize off the top is the Rockefeller Institute of Government. What an operation. Now they happen to be about 100 yards from my apartment. So I occasionally visit them, but this is not why I'm biased towards them. I'm biased towards them because I have a stack of really high quality reports on my desk and I have a lot of reading to do. And so it's a pleasure for me to see you guys here working with our Department of Atmospheric Sciences. The second thing I want to say is about us. And that includes the ASRC and the National Weather Service. You know, people say everybody talks about the weather and nobody does anything about it. Well, we can't control the weather, but the University of Albany is doing something about it. We're up to how many now? 106 weather stations that we've built? 108, right? You can't keep up. We're going to 125. They're everywhere. I mean, SUNY says that it has a university or community college within 30 miles of every New Yorker. That's 64 campuses. We're going to have one within every 15 miles of a New Yorker, or something like that. And why is this important? Because if we can't change the weather, we really should know about it. Towns need to know whether to spend money to get ready for that snowstorm, or whether that finger effect of the lake is going to be 6 miles north and you'll have an inch. You waste your money. Or worse yet, you're not ready for something that happens. I know how this works personally. I was in a slightly different state, New Jersey, when Hurricane Sandy did $80,000 to our family beach house. $80,000 damage. We have recovered. As New Jersey likes to say, the Jersey Shore is back and stronger. It's probably true. But I think what we really would have appreciated was more intelligence about when this was coming, about what to do about it. Now, because it was such a big event, nobody really missed it. But I think hyper-accurate weather prediction is fundamental to the future. And I think we, at the University of Albany, working in partnership with the state of New York, are going to build the best weather prediction system in the world. And we're going to do that. And that deserves a round of applause for these guys that are doing it. Now, another thing that happens, and this is part of this connectivity, is this system is incredibly rich in data. And there's all kinds of data analytics that we can do about it that Jim Diaz's VPR has been pushing for years in multiple fields. We're starting to respond with programs. The math department is beginning to change the way it thinks. And I apologize to mathematicians in the room if I'm talking out of school here. But get a little bit of math involved in enhancing data analytics, because it's not just about executing the formulas, it's about having better formulas. And this applies everywhere. It applies to medical data. It applies to the Attorney General's office and FOIL requests. It applies to things that maybe we don't want to talk about, like the way the government mines my Facebook account to see if I'm about to do anything that they don't want me to do. But the point is that it's a national issue, and it leads me to my last point, which is that for those of you that are in the room from industry, if there are some of you here, it's very important that we as a university, working with the state, working with the Rockefeller Institute, find ways to get out of the ivory tower. Now, if you think this isn't a problem, I have to correct you. I spent my entire life in higher education, and the ivory tower is an insidious prison. It's a wonderful place to live. It's like being in the monastery. Everything is taken care of. You can just concentrate on translating that text from Greek to Italian or whatever it is you're doing. It's a great life. It's very seductive, but it's not the life of a public university. It's not the most productive and effective way to be. We simply must get out and use the data we have, the techniques we've learned, the skills we have, in order to form partnerships with private entities while we maintain our integrity and stay on the right side of the legal line, in case you're worried about that, but nevertheless execute so that we can, as a university, be stronger. And then the last point I want to make is that everything we do here, which we do primarily for ourselves, out of our scholarship, out of our depth in scholarship, we translate out to our students. There's 17,000 of them outside these walls. They're looking to us to help have an impact on their lives, and we are looking to you to help them find ways to put that knowledge that we're teaching them in the classroom into works. We want to go beyond a biology lab, which is my field, where a student works in a controlled environment, and put them in a biology company, where they could make a mistake and cost the company thousands of dollars because they mixed their reagents wrong and they led them down the wrong path. That kind of real-world presence, that kind of possibility, and we hope none of our students ever make a mistake in any of your companies, is what gives it an authenticity that we know gives them more resonance back on the campus, makes them better students here, and makes them better able to get jobs when they graduate. So it sounds like it's almost anti-intellectual, but we're going to focus not only on sending kids to medical school and law school and graduate school and turning some of them into professors just like us, but we're going to focus on getting them jobs afterwards, using the main factors that we have, like all the stuff that's in the conversations you'll be having today, to get our students jobs so that we really are known as the engine of opportunity. And we want to be a national leader in doing that. That backs up to the public-private partnership. That backs up to the intellectual efforts that are underlying our conversation today. That backs up with partnerships with places like the Rockefeller Institute. And that's probably going to lead to another report on my desk that I'm going to have to read and come down and talk to you guys about. Thank you so much for being here.
Morning, everyone. How about another round of applause for Jim Steller, the new president here at UAlbany. Thank you very much. I also want to thank Bob, Kris, and the University at Albany for asking me to take part in this year's Severe Weather Conference. When it comes to severe weather, climate, the correlation between the two, and how the public prepares and responds to varying degrees of events, I find myself in a unique position. Having graduated from UAlbany's Atmospheric Science Department, I have an understanding of the science that goes into making these predictions of severe weather. But being a TV meteorologist, I also have the task of distributing that information, and often complex information, to the general public, and in many cases, the first responders, some of which we have here. While a 2 to 3 minute weather forecast is not always the best way to get the methodology out, it does allow us enough to give a synopsis so that the large mass of people out there are getting the vital information they need with an approaching storm in a short period of time. So we do have that. But it is a conference like this where we can discuss the theories and the processes behind where many of these forecasts originate. So again, I'm happy to take part in this forum, and I also hope to learn a few things today because I know some of the presentations are going to be fantastic. One of the questions I'm asked when I'm out in the public is what kind of winter we're going to have. I mean, it's inevitable this time of year. You go to the store, you go to the bank, and I'm sure many of you are thinking the same thing. So with this lineup of presenters we have here today, I'm sure we're all going to leave here today knowing exactly how much snow we're going to get by the time the winter's over. So I look forward to that as well. So we'll get the program started. Our first speaker is Dr. Kris Thorncroft, who is a full professor and department chair here at the University of Albany of the Atmospheric Science Department. Dr. Thorncroft's research mainly is focused on improving our understanding of natural variability of atmospheric weather systems with a special emphasis on tropical weather systems over West Africa and how they impact Atlantic tropical cyclones or hurricanes. He also researches the causes of extreme weather variability, which we're aware of here in the northeastern United States, and that includes landfalling hurricanes. Dr. Thorncroft is also co-principal investigator for the New York State Mesonet, which we talked about, a network of eventually 125 automatic weather stations that will make key weather observations across the whole state. We mentioned one within every 15 miles of a resident of New York State. So we want to thank him for that and also welcome him here for his talk. Kris.
Where are we? Where is it? Go. Where? Can't see anything. It's there. I know it's there. Oh, there it is. God. Finally. Okay. Are we good? Good. Okay, thank you. Okay, thank you for the introduction, Paul, and thank you for agreeing to help us out today. This is the third such event where we are trying to exchange some of our knowledge and information about the causes of extreme weather, but also how climate is changing. The first one of these events was more dealing with climate change itself and trying to educate and inform about the processes that involve climate change and how it's affecting us. The second one, we tried to have a theme that introduced the idea of probabilistic forecasting, the idea that there's always there's some level of uncertainty in a forecast, and that we have to live with that. Some forecasts, some less certain than others. Today's theme, although it's more general now, I wanted to introduce the idea of natural variability. So in addition to some climate change forcing, which provides a long-term trend to temperatures on the planet and other aspects of climate change, we are always going to be impacted still by natural variations. And two such natural variations affected the winter last year. One was El Nino, and one was the so-called Polar Vortex. So that's why we're going to be discussing those two topics, because they had a big impact on last year's winter. So keep calm and stop global warming. So my talk is actually going to set up the talks to come, but I also wanted to remind people about climate change because of its importance, and we mustn't forget climate change and how it's impacting. This is a political slide. So this is some sculpture, I think it's somewhere in Europe, depicting politicians discussing climate change, even though the water's rising up to their shoulders. I also like to make this point. Does that come across very well? I can't see it here. So anyway, the topic there is some misconceptions in the public are regarding the disagreement between people over whether climate change is happening and whether humans are affecting it. Media and politicians like to promote, through their actions, a 50-50 split on the idea of climate change. But if you talk to people that know what they're talking about, climate scientists, the agreement is 97% plus. So climate scientists don't agree about anything, but they agree on this topic. So there is human impact on climate, and it's certain that humans are impacting climate over the last century. And so that has to be borne out. When you see the media or hear the politicians talking about it's not right to just choose one or the other. It's not valid. There are facts out there that, if interpreted correctly, lead you to the conclusion that there is man-made global warming. So I'm going to show you an animation here just to highlight what's happened over the last century. These are temperature anomalies with respect to the century average temperature. So blue means cold, and yellow means warm. And it'll eventually get redder in the yellow area, which means it's getting even warmer. So, so this is from the end of the 19th century, and it's going up in 5 years. You can see it's blue and yellow. Actually, it's cold now at the beginning of the 20th century. You'll start to see a little bit warming. It's kind of a noisy field. The northern polar region is actually getting a little bit warmer than other regions, for reasons we understand. And we're into the 70s, 80s, 90s, the last 10 years. And this is where we are. So we have a red planet now. So the planet's warmed up by more than a degree over the last 100 years or so. So let me get it up to date. This was 2015. The year 2015 was the warmest the planet on record. It's the warmest year on record, and you can see obviously a lot of. Let's see if I can get this going. There's red or pink over here indicating a warm. That's consistent actually with the El Nino pattern, which Paul Roundy will talk about in a minute. But actually, it's quite red over much of the globe and the planet. What's interesting is that for those of you who are 30 years or younger, you haven't seen the planet colder than the 20th century average. So the last time the planet was colder than the 20th century average was in February '85. Ever since then, we've been warmer than the average for the planet of the 20th century. To highlight that a little bit more, these are the top 10 warmest years on record since the end of the 19th century. And you can see, well, 2015 is up there. We're up to about 0.9 degrees, 1 degrees. And you can see that all of the years have occurred this century except for one, which I think was the end of an El Nino event, actually. So, it's getting hot, folks. So this is a time series depicting that global temperature change. It has the same information in here, more or less, that we had in the animation, except it's now one single value of temperature for the planet. And you can see this is the trend that we saw in that animation. You saw towards the end of the animation, the whole planet was getting more yellow and orange and definitely heating up towards in the last half, particularly of that century. Now, I'm not going to talk about the causes here except, or show you proof of it, but this warming is entirely consistent with the increased amounts of greenhouse gases in the atmosphere, in particular associated with carbon dioxide. And this is what I mean about the scientists agreeing on that. 97% plus of the scientists agree that this warming trend that we've observed is consistent with the greenhouse gases that we're pumping into the atmosphere. So today's theme, I wanted to get onto something to do with natural variability, and I think you'll notice that maybe if you're ultra inquisitive, it's kind of a noisy there's lots of ups and downs on here, and it's not complete. There's some meanderings here. It's not a straight line. Although carbon dioxide is actually a pretty much straight line increasing over the last century or so, there's a lot of ups and downs in this time series. So why does it go up and down? And the answer is there's a lot of natural forcing. There's still a lot of natural variability. So the right way to vision the global temperatures is there's a long-term trend associated with global warming and increased greenhouse gases. But there's year-to-year variability associated with phenomena that we understand, and that will always be the case. So one sort of natural phenomena are the volcanoes. The big dips that you see here are associated with volcano eruptions, and volcanoes spew out a lot of ash and dust and pollution into the atmosphere, and sometimes it can rise up into the stratosphere and actually stop solar radiation coming into the planet. And so on those years where there's significant major volcanic eruptions, this is Pinatubo, by the way, you can actually cool the planet for months to a year or more. But it's not going to affect the trend. It'll just bring you down for a while. And it's important to be aware of those things because the media might go, okay, there's no climate change or something. The other big signal on this up and down time series are the El Ninos, and we're going to hear more about that in a minute. But the big peaks here are associated with El Ninos. El Ninos are associated with a spread of warm water across the Pacific and actually affects the temperature of the whole planet for a year or two. And so that impacts the global temperature. So dips can be associated with volcanoes. They can also be associated with the opposite of El Nino, La Nina, but they can also be associated, the peaks are associated with El Ninos. Whenever you hear an El Nino coming, it's very likely that that year is going to break the record in terms of temperature, because we have a trend in warming, and then you add El Nino, you just add a little bit more heat, it's going to break the record, and that's what happened last year. That's why 2015 was the warmest year on record. So it's part of a long-term trend, and you have an extra bit of boost from El Nino. Okay, let me give some more background on New York, and then let me get into introducing the next speakers. And so this is background again, just to highlight the fact that we've seen warming this actually shows the trend or the change in temperature over the last century, more or less, and just highlights the signal over the US. So, and it's consistent with that global temperature. So in all the different regions, some it's less clear, but in the Northeast, we see a warming over the last century, and over much of the US, we see a warming. This is kind of the future now. That was the observations. This is the future, depending on how much CO2 we pump into the atmosphere, and it's very likely we're going to continue to pump CO2 in the atmosphere, I'm afraid. Our temperatures by the end of this century are going to be similar to what we have in Georgia now. So imagine what it's going to be like in Georgia. More background in terms of extremes associated with the warming of the atmosphere. Atmosphere tends to have more water involved, more water vapor, and that can actually increase the intensity of the weather systems that give us rain and strong winds. As a meteorologist, I'm excited by this figure, but this is a serious figure because it shows. This 74% value shows you the change in the frequency of the most intense rainfall events that have impacted the Northeast over the last century, over the last 50 years, sorry. And this is an observation, this isn't being made up. So we have observed a change in the frequency of intense rainfall events, and more so here than anywhere else in the country. So perhaps even more so here, we need to be prepared for extreme weather, consistent with that. And that was a major motivator for the Mesonet. So what about this winter? And let me get you into the upcoming talks. This past winter. So this was actually showing you you can see the color. This shows you the ranks for whether records were being broken. Solid red here indicates that region showed a record temperature for December. And you can see, first of all, in the Pacific, a lot of records were being broken in association with El Nino. Again, it's El Nino plus global warming, if you like. That's why we have a breaking record here. And we can see a lot of records were going in the eastern side of the country. Also, a lot of records going across the whole of the tropics, and a lot of that signal across the tropics was also linked to El Nino through some teleconnections. So what happened in the US? This shows you the December temperature anomalies. We have 10 Fahrenheit, and we can see the eastern side of the US was, I'm sure you remember, it was very warm. I mean, so this was what we had to deal with last year. Quite significant. So very warm in the east, somewhat a little bit chillier, but closer to average in the west. So let me just say something about extremes. More general, this is a general thing, but it's kind of relevant also to the extreme winter temperature. In terms of climate change, you can't blame one extreme event on climate change. It's hard to do that, although there may be a contribution from climate change. Climate change is expected to be manifested in terms of an increased frequency of extreme events. And I like the analogy here of a baseball hitter. Baseball before steroids would hit home runs occasionally. So you'd have an extreme event. Pump them up with steroids, and you're going to get more home runs. So which one was associated with the steroids and which one was associated with natural ability, you can't separate. So when we're talking about climate change and extremes, we're talking about the change in frequency of extremes. Although there is a body of research out there that attributes climate change to any particular event, and that's something that's kind of interesting. So the warm winter last year may have been part of a global warming signal, almost certainly was, but it certainly was contributed to from natural variations. And the two smoking guns, if you like, were El Nino, which Paul Roundy is going to talk about in a second, and the Polar Vortex, which Andrea Lang is going to talk about afterwards. So this next two talks are more about the natural variability and how it impacted last winter and may affect this winter. The second part of this work, of this presentation, is going to be associated with how we deal with extremes. And this is, again, my favorite picture. We better be thinking about how we deal with extremes. So why we should do all we can to curb the emissions of greenhouse gases to stop or limit as much as we can the effects of global warming, we have to be prepared for what lies ahead of us in terms of extremes. So the talks in the second half are Everett Joseph is going to talk about a quite prestigious project involving research that links forecasting and better decision making. And then we have Ray O'Keefe, who's going to talk about weather forecasting in the region, and David Valley, who's going to talk about hydrological forecasting. And I'll end up with my favorite slide. You may have heard of this. You may have heard of this movie. An Inconvenient Truth, but a lot of people like the reassuring lie because it makes us feel comfortable. And the reassuring lie is telling us that we don't have to change our lives, where in reality we really do. But okay, thanks. Good luck with that. Should we try and get. No, I've learned how to do it.
Thanks, Kris. I should mention, I failed to do that at the beginning, that we are going to have a question and answer session after the first 3 presenters, and we'll open it up, and then after the second 3 presenters, we'll do the same thing. So we're going to move on to the next 2 presentations, and then we'll have our first question and answer session. This one is from Dr. Paul Roundy. He's an associate professor at UAlbany's Department of Atmospheric Science. He holds a PhD in meteorology from Penn State University and a Bachelor of Science in Physics. Dr. Roundy studies how thunderstorms organize in the tropics, focusing on signals that last from days to as much as years. His recent interests include research to better understand how the global atmosphere responds to and interacts with the organized thunderstorm activities in the tropics. So Kris had already outlined a little bit about what Dr. Roundy's going to do now. We'll get his presentation. Thanks.
Thank you. Thank you. So this is my house last December. I've got an orchard in the front. Let's see if I can figure out. There we go. I've got an orchard in the front that's covered with mulch. What you see there is not snow. The lawn is still green. My 8-year-old son at the time had gotten excited about Christmas time and pulled out the sleds and said, well, maybe not. On Christmas Eve, it was 70 degrees. And we played Frisbee. That season, as Kris already showed you, there were a number of records set at many stations across the eastern United States and other places around the world. You see here the rankings at many different stations. Number 1, this is not just number 1 for individual days in December, but number 1 for the December average overall. Quite extraordinary. The average temperature, this is in degrees Celsius this time, was greater than 8 degrees above average in New York. This is 15 degrees Celsius. Again, it's not unusual to find individual days or a few days in a row that have temperature departures from normal greater than these. But to have this kind of displacement or difference from normal averaged over an entire month is extraordinary. Now, to put this in perspective, this is the diagram of the difference between the average temperature in the decade from 2005 to 2015 and from 1970 to 1980. This is suggesting a pattern of warming in the northeastern United States of order a couple of degrees Celsius. This is a factor of 3 or 4 smaller than what actually was observed last year. Shows that at least on a regional scale, the variability in temperature due to natural phenomena still greatly exceeds the long-term trends associated with climate change. Now, a leading contributing factor to this warm signal in December last year and through most of the winter was the El Nino pattern. In order to understand El Nino, we need to consider patterns of sea surface temperature around the world. And this is sea surface and land surface temperature, but you can see over much of the tropics, there's a region called the warm pool here, extending from the Indian Ocean to the Western Pacific. We expect colder temperatures at higher latitudes. So imagine yourself on a ship off the west coast of Washington State, and you're taking measurements of the sea surface temperature, and you're heading south. And we'd all expect, I think, as we head south, the temperature increases with time and distance until you get down to around 7 degrees north, at which time you reach a maximum, and it surprises many people that the sea surface temperature actually begins to decline as you approach the equator. The reason for this is that over the Pacific much of the time, there's trade winds blowing from east to west, and these trade winds pile up warm water in the western basin, and because of the rotation of the Earth, they upwell cold water from below, leading to colder temperatures right on the equator. Now, the El Nino condition is what maybe most of us would have expected in the absence of that upwelling, is that the equatorial region is warmer over much of over the entire Pacific basin. This is an unusual condition. It's important to the way the atmosphere behaves because it redistributes rainfall. Rain in the tropics tends to occur. It tends to favor the regions that are warmest. Not always, but it tends to favor those regions. Now, because El Nino has such a striking impact on the world economies, the global atmospheric circulation, and our weather, we have placed buoys in the Pacific Ocean to take measurements of the atmosphere and ocean conditions, so we can track these conditions. And with a set of these buoys, we're able to develop diagrams, plot maps of the distribution of the warmest water. This is a cross-section of temperature. Think of it like you were south of the equator in the ocean looking to the north, and like you dyed the warmest water red and the coolest water in blue. Sorry. I'm going to go back one. And you find that on the large scale here, warm water floats on top of the cold water, and the trade winds blowing from east to west will pile up a region of deep warm water in the western basin while upwelling the colder water in the eastern basin. And then this is the El Nino condition last year. So extraordinary eastward spreading of the warm water, so that now that warm water is exposed to the air in the atmosphere over more of the basin. We'll get into the impacts of that in the atmosphere in a moment. So this is a map of the difference from normal ocean surface and land surface temperature for December through February of last winter. We find this region right here, everything above this contour is greater than 1.5 degrees Celsius above average. Some of the regions last year achieved their highest temperatures ever observed, making this, at least by some measures, the strongest El Nino event ever observed. Now, as I mentioned already, the rainfall in the tropics tends to distribute in the region of the warmest water. And last year was not much different from that. The intense rainfall in the tropics here is associated with thunderstorms, deep cloudiness that extends from the lower atmosphere very high. And condensation in these thunderstorms heats the atmosphere and causes it to spread to the north and to the south. So here I've drawn on some wind vectors, again, differences from normal. We can see the wind spreading away from the region of convection, and that disrupts the normal atmospheric flow. And because of the rotation of the Earth, the wind blowing away from those regions of thunderstorm activity gets torqued by the rotation of the Earth into this subtropical jet stream, which blows warm Pacific air into the western part of North America. Now, in addition to that, there's a standing wave response in the atmosphere. You can think of these as waves in the atmosphere that are the size of the planet itself. A trough set up over the North Pacific, we'll call it a blocking ridge over Canada, and a trough again over the Atlantic Ocean. The air circulation around these patterns draws in warm air from the subtropics into the interior of North America, resulting in higher temperatures just because of the source of that air. But in addition to that, the circulation patterns favor snowfall in some areas and disfavor snowfall in other regions, so that in the areas where snow is unusually low, the incoming solar radiation, instead of being reflected into space, is absorbed, and this produces enhanced warming above the effect of the transport of warm air into the continent. So now we understand last winter. Let's think about the implications to the trend in climate change. Although these are natural variations, El Nino has been going on and off since the time of the decline of the dinosaurs, since the Pacific Ocean was wide enough and the warm layer on the surface of the Pacific Ocean became shallow enough that cold water could be drawn up to result in El Nino-like fluctuations. So Kris has already pointed out that several of the highest temperature events that we observe in the global average were associated with El Nino. I once attended a climate conference. This was back in 1999, so just right after this event, and climate scientists were plotting these diagrams with their trend lines ending in 1998, and they were really excited about those outcomes, thinking it strengthened their arguments. They didn't mention, and many of them did not consider, the impact of the El Nino. In contrast, now after that time, skeptics have been able to take hold of this relative lack of a trend since 1998, simply because the conditions became so warm that year. If you removed those events, then there was a gradual upward trend all the way through the period. Now, here's just simply reflecting on the diagrams we've already seen about why this relationship to global temperature occurs with El Nino. El Nino distributes the warm pool over a broader region of the world, allowing the ocean to transfer its heat to the atmosphere. Looking at the temperature cross-sections that I already showed you, El Nino, again associated with eastward movement of the warm water, spread over a larger region of the world. Now, El Nino is gone for this year. Some of its signatures remain left behind over the northern tropical Pacific Ocean, where there's still warm water left behind here, but cold water has begun to emerge in this region along the equator. So we expect different patterns this year, but that doesn't necessarily mean that one should expect cold and snowy outcomes. This year, rainfall in the tropics is occurring over the warmest water regions here, over the far eastern Indian Ocean, the maritime continent, and the western Pacific. And as with El Nino, the signal heats the atmosphere and results in construction of ridges, high pressure areas to the north and the south, and a wave train that produces weather outcomes downstream. In particular, this region right here, this trough over the North Pacific, is associated with transport of warm, moist air into the Arctic, which has prevented the formation of ice in some regions over here. One of our leading sources of cold air in North America is this region of Siberia, where the transport of the cold air on occasion can come across the Arctic and then east of the Rocky Mountains and down here. At this point, we don't have that source of cold air because of the break in the ice, which is part a climate change contribution, but also because of this extraordinary wind forcing driving warm air from the south into that region. And I'll stop here after a comment on what this implies for the upcoming winter. Convection over the maritime continent region and so this region right here and across this region of the North Pacific is associated with later in the winter trough anomalies here and ridge anomalies down in the southeastern United States. I would argue that there's potential for conditions to be colder this winter. It's a pretty strong potential just because of how extreme last year's outcomes were. But don't read that to imply that the background conditions favor extremely cold and snowy outcomes. They don't appear to, although the risk of cold events is higher than last year. So I guess in the questions I might be able to address a little bit more specific about the forecast. Seasonal forecasts made by many organizations out there don't show much skill. And it's important that we take them with caution because although they might be able to take into account slowly evolving patterns in the global atmosphere and the climate, they don't take into account events that yield transitions and changes in the weather pattern that can affect the averages over the season as a whole. Thank you.
Our next speaker is Dr. Andrea Lang. She's an assistant professor here at UAlbany's Department of Atmospheric Science. Dr. Lang began her tenure at UAlbany here in 2012 after receiving her PhD from the University of Wisconsin-Madison. Dr. Lang's research interests span weather systems of the mid-latitudes to large-scale dynamics of the troposphere and stratosphere on timescales from days to weeks. She is the co-lead of NOAA's newly formed task force on subseasonal to seasonal prediction.
All right, thank you. So today I'm going to extend some of the comments that Paul has made about this winter's forecast and also talk a little bit about last winter. But one of the things that I want to do before I really get started is talk about this term, the polar vortex. And a lot of people have heard this term. It's been used in the media lately, in the last few winters. And it's really something that has come to societal attention recently, but something that scientists have been thinking about for a long time. So today I want to talk about some of the facts about the polar vortex and some of the things that may be myths or more like fiction. So over the last few years, we've seen a lot of this on the media. So there's been, you've seen the meteorologist go outside in the middle of the polar vortex that attacked Chicago in 2014. And you saw them taking cups of water and throwing it into the air, and then it was coming down as ice. So there was some of that, hype of this idea that there's a polar vortex. So this idea, there's a lot of interesting things that you can do because it's so cold outside, but really, the polar vortex, there's a science behind it, and there's things that we can actually describe about its evolution. So I'd just like to say that, the polar vortex doesn't attack cities. It doesn't, it's not something to be scared of. It's something that forms naturally and evolves every given season. And so just to point out, I was part of this. I went on the Weather Channel to talk about the polar vortex, and I tried to bring some of this perspective from the science side to the public. I also want to mention that it's been, as far as societal impacts of the polar vortex. One of the things that I found interesting was about 9 months after the polar vortex attacked Chicago, there were reports of a local baby boom. So there are societal impacts to the polar vortex that extend beyond the weather. So I mentioned that the polar vortex is something that has been described scientifically for a long time. And I think it was actually Al Roker who tried to bring this to people's attention in one of his tweets from that winter of 2014, where he said, for all the doubters who say that the media created the polar vortex, this is an excerpt from the glossary of the American Meteorological Society, and it's from the glossary that was published in 1959, and he just highlighted the polar vortex and described it as a westerly circumpolar circulation around the mid and high latitudes of the planet. So you get a polar vortex in the northern hemisphere, and you also get one in the southern hemisphere. So what is this polar vortex that we're talking about? So how does it develop? So when we talk about the polar vortex, it forms in the winter, and it forms because on the average, the Earth is rotating around the sun, and the Earth is rotating on this tilted axis. So during our winter in the northern hemisphere, the axis of the Earth is tilted away from the sun. So what that means, if you've gone to Alaska or some European country during the winter, you know that you have very short daylight hours and long night hours. So essentially, the sun shines more directly on the southern hemisphere during the winter, our northern hemisphere winter, and we receive little sunlight in the northern hemisphere. So that allows the polar regions to cool faster in our winter than some of the more temperate regions of the planet, the mid-latitudes. So what does this do? If you were to take this idea and now imagine looking down at the Earth to the North Pole, we would see something like this. So what I've done here is I've taken the temperature at every latitude of the planet and averaged it. So we get this nice circular picture. And what you see is that we have, in the wintertime, really cold polar temperatures, and then warmer gradually as you go out towards the equator. So what this means is that there's a thermal contrast from the pole to equator, and this means that as we go up from ground upwards into the atmosphere, the winds are going to increase with height. So around this contrast in temperatures that we get because the polar regions are colder naturally than the equatorial regions, we get strong westerly winds encircling this cold air. So what we see is that if I were to plot winds on this, I've shaded winds that are greater than a certain magnitude on average around each latitude belt. So in this diagram, the regions where you see that strong temperature contrast are the regions where you have the strongest winds at upper levels. So in this case, because we get colder as we go to the pole, this tells us that this wind has to be westerly, coming from the west, blowing to the east, around this mid-latitude part of the planet. So how does this relate to the polar vortex? Well, it turns out that the polar vortex is found at upper levels in the upper troposphere and the stratosphere. So what I mean by this is from about 5 kilometers upwards into the stratosphere, about 40 kilometers. So the polar vortex is associated with cold air in its center, but the winds associated with the polar vortex exist from about 5 kilometers in the atmosphere to about 40 kilometers. So the polar vortex can impact the weather that we experience at the ground. So yes, it's associated with the winds and the cold air in the 5 kilometer to 40 kilometer range, but its evolution can impact our weather as citizens that live on the planet's surface. So my research is focused on how we get this polar vortex and its evolution to impact our weather. So my research is the how this happens. So one of the ways that we describe the evolution of the polar vortex is we describe its strength. So in talking about the strength of the polar vortex, one of the metrics we commonly use is the wind speed in this circumpolar version of the polar vortex. So if you have stronger westerly winds at the 5 to 40 kilometer range, then you have a strong polar vortex. If they're weaker, then you have a weak polar vortex. So it turns out that tracking the strength of the polar vortex can give you some indication about how it's going to impact weather anytime from now to 90 days from now. And this is, again, when the polar vortex is present, which is during the winter time. So here I have an evolution of one of the depictions of how we track the evolution of the polar vortex. And what this animation is showing you is a depiction or a slice through the top part of the polar vortex near that 40-kilometer region. So if I were to look, we're taking an animation of what's going on at the top of this polar vortex, and this is what it looked like during the winter of 2012, 2013. And what you can see is the polar vortex at the beginning of this animation started as very circular, but now you can see that it's being stretched out, being pulled in different directions. And if you were to think about the winds, you can imagine, you see this movement, it's associated with winds. You can imagine that we no longer have strong westerly winds around the pole anymore because the polar vortex is being stretched out. So what we're looking at here is the evolution of the polar vortex going from a strong state to a weak state. So the strength of the polar vortex in the stratosphere is linked to weather impacts 1 week to 90 days later. So this idea of tracking the strength of the polar vortex in the stratosphere gives us an indication of what weather conditions might be like in the weeks to roughly month time scale. So this is the sub-seasonal time scale. We're not talking about what things might be like for the entire winter season, but on the sub-seasonal time scale. So if we were to look at this, we can conceptually think about what the polar vortex might look like. And I apologize, you can't, the projector is a little bit dim, but what you're looking at here is the northern hemisphere and a depiction of a strong vortex that's nice and circular around the North Pole and a weak polar vortex that has a lot of waves in it. So we're looking at the westerly winds that are nice and circular in a strong vortex and keeps that cold air over the pole. And in a weak vortex, we have a wavy westerly jet at upper levels, and cold air is more likely to be displaced off the pole, but warm air is also more likely to go poleward and impact the pole. So Paul mentioned wavy atmospheric conditions, thinking about waves in the flow, and the polar vortex is definitely described by the magnitude or the amplitude of those waves along that jet around the pole. So for those of you that look at forecasts, this state of the polar vortex is definitely linked to an oscillation called the Arctic oscillation. During the positive phase of the Arctic oscillation, we see strong polar vortex conditions. During the negative phase of the Arctic oscillation, we see wavy conditions. So in this case, during the negative phase, during a weak polar vortex, we see a higher likelihood of cold air moving to more southern latitudes and warm air moving to more northern latitudes. So during the negative phase, during a weak polar vortex, you're more likely to see the probability of cold air outbreaks is greater, and the probability of extreme weather, stronger winter storms, is also going to be greater. So I talked about, thinking about the polar vortex in the stratosphere and how it impacts weather. So another thing we do is we look at the strength of the polar vortex at various heights going from the surface all the way up to that 40-kilometer level. So people have looked at the data and the data that we have in the reanalysis data from the 1950s to present, and in that data there have been a certain number of weak and strong vortex events, and we can composite those together to look at how they evolve on average. So what we're looking at on this plot is a composite of weak vortex events, and let me describe these to you. So what you're looking at here is there's a line down the middle representing the date that the weak or strong vortex was identified. So what you're also looking at is days leading to that event and days after that event. So leading to that event are on the left side, after that event are on the right side, and then the vertical axis of these graphs are showing you the height above ground level that we are measuring this weak or strong vortex. So the takeaway from here is that if you measure a weak vortex in the stratosphere, sometime in the roughly 0-day to 60-day time frame, you're going to see weak vortex conditions reach the ground So after a strong vortex, you also see the same thing. Those strong vortex conditions reach the ground in some timeline between 1 week and 60 to 90 days afterward. So what goes on in the stratosphere has implications for what goes on at the ground level. So understanding how that happens is the research that I work on. So understanding how you get the weak vortex event in the first place. So to give you some idea about that, we have this graph is again showing you altitude along the vertical, and then along the bottom we're looking at time. So what happens is you need some wave to occur in the troposphere, in the ground, in the surface conditions, and those waves can be produced by El Nino conditions like Paul mentioned, and those waves can sometimes propagate upward. And when they propagate upward, they amplify in the stratosphere, something causes them to break, and then you can get something called a sudden stratospheric warming event, and that's weak vortex conditions. That then causes this chain of reaction that allows these signals to descend from the stratosphere to the troposphere with time. So the height that this sudden stratospheric warming occurs tells you how long in that subseasonal time frame that these conditions will last. So what I'm showing you here is the temperature anomalies during weak vortex conditions. So this is looking at the time frame 30 days averaged before a weak vortex event and to 30 days after a weak vortex event. And essentially, before a weak vortex event, we see warmer temperatures, especially in Canada, but also in the Northeast. And as we move through this, going into after a weak vortex event, we start to see the southeast US get cold. And here in Albany, in New York State, we tend to be on the cold side of these averaged conditions. So weak vortex events can impact the temperature here in New York. So moving on quickly, we can also do something similar for strong vortex events. It turns out that during strong vortex events, it's not the exact opposite, but we typically also see colder conditions. So I don't have much time left, so I will end. Oh my goodness, that's not how this graph is supposed to look. But I just wanted to mention that, let's see. All right, so the takeaways, 2015-2016 winter, last winter, we had extreme strong vortex conditions, which led us to be slightly warmer here in New York State. This year, as we're going into the winter season, we have extremely weak vortex conditions. That means that wavier conditions in the atmosphere, more likelihood of cold air descending from the north and warm air coming from the south. So the forecast currently is very uncertain, but it doesn't look like the vortex is going to strengthen anytime soon. So I'll end it there.
Very interesting. All the presentations, fantastic. I'm going to open this up to questions now. We have a mic in the center of the room as well, or that's where we'd like you to go. If you have a question for any of the three panelists and their presentations, if you need help with the microphone and you can't get to it, we'll have somebody bring it to you. I think we have a mobile mic as well. I'm going to start the questioning because I have a question for Andrea. And I really enjoyed the animation you had of the cross-section. But you could also see how haphazard it was and sort of looks unpredictable. It's just like some taffy being spun up, which is pretty remarkable. I look at these things all the time as well. How could we tell, as a forecaster, or as somebody who follows the forecast, when we do see a weak polar vortex, where that cold air will drop down from the pole? I mean, it can drop down, it seems like when you look at that animation, over Europe or over Asia or here in North America. What is the signal that we can look for, if any, here in, let's say, North America, or better yet, here in the eastern United States, that weak polar vortex will lead to colder air dropping down for us?
That's a I don't know if these are on. Are they on?
I think so.
Okay, so that's a really good question. And the one thing that I'll say is that the large scale flow determines whether or not we'll have a weak or strong vortex event. So we're really good at, well, I wouldn't even go with really good, but on the subseasonal timescales, we have fairly good models in saying that the vortex will either be weak or strong. What is still on the weather timescales, so we have a lot of uncertainty and it's more like weather timescales, is how and where those different lobes of the vortex will go. So there's currently a project going on, and I'm part of this project, that is looking at how well we resolve these weak vortex events in forecast models. And right now, we have fairly good skill on the order of 15 days. And we don't actually resolve them in a forecast leading up to the event, but what we do really well is once the event has occurred is being able to resolve the impacts. So it's one of these things that once we know it's going to happen, then we can do a good job of describing the outcomes, but forecasting whether or not it's going to happen in the first place is still something that we're working on.
Thank you. Anyone else have a question here? I see. Okay, go right ahead.
Thank you all very much. I learned a lot from your talks. For Dr. Roundy, I just wanted to clarify the association between the natural phenomena like El Nino and global warming. On part of it, it sounded like you were implying that they're separate, and that in regards to a particular year, the variation is driven much more by the natural phenomenon than the global warming. But other times, it seems like you were implying an interaction, particularly when you mentioned this El Nino was the worst on record, and perhaps that's not coincidental. If the sea surface is already higher from global warming, then perhaps that makes it more likely to have that severe an El Nino.
So thank you. This is a complicated problem, and I think it's understanding of interactions between things like El Nino and weather events and climate change is still really a science in its infancy. We're gaining some understanding of, I think just in the last few years, some improvements in climate model simulations of El Nino, but none of them do a particularly good job yet in simulating the real weather events that kick the ocean or impact changes in the structure and amplitude of an El Nino event. And so it makes it really complicated to really draw a clear inference about, well, what is the real influence of climate change on El Nino? You gave one reasonable example, and that is if the ocean temperature as a whole is rising, then maybe that increases the amount of energy available for these events. But the Eastern Pacific, equatorial Pacific, is not really warming. The Indian Ocean is warming. The Western Pacific may be warming. That would look more like an adjustment toward a La Nina condition, a colder ENSO condition, but some models seem to suggest conditions looking more like El Nino into the future. So there's really an enormous amount of uncertainty. I think it's plausible that we'll come to an understanding in the next few years, hopefully, that we'll be able to make some clear arguments about these things.
Can I just add, it's definitely an interesting question to ask about how the nature of extremes will change in the future. And as Paul says, there's a great deal of uncertainty. So unanswered questions could be, do we expect more intense El Ninos in the future? Do we expect El Ninos to be more frequent in the future or even longer lasting in the future? I think there's uncertainty about those. So there is definitely, we expect an interaction between climate change and El Nino, but a lot of the questions remain unanswered about how that's going to be manifested.
The observational record is confusing on this issue because there were more stronger El Nino events closer together in time between the 1980s and the 1990s than there have been since. Random variability associated with the weather kicking the ocean generates more amplitude variability in El Nino events, probably, than climate change, or we would see an evident trend over time. Where we've got one strong event since 1998.
Thank you. Do we have any other questions for any of the panelists? Yeah, go ahead. We'll wait.
Exercise.
It needs to be recorded.
Come up here.
It looks like there's several things that we're developing in order to improve our ability to predict the weather. The mesonets are important, the polar vortex, the El Ninos. How do we have any sense of how much we need to understand each of those in order to improve, or how much they've been integrated into our current forecasting methods?
I won't answer that question, but I'll clarify it. So one of the things that you meant, that there are different timescales involved, and I think it would be worth emphasizing that El Nino is part of a 2 to 7 year cycle, so is important for El Nino sort of sets up the season. There is variability in the season, but El Nino is more about, we can look at the state of the Pacific Ocean, and there is a forecasting activity that tells you about what's going to happen in the coming season. The Polar Vortex, as Andrea said, actually is thinking about more shorter timescales. So you could, up to 90 days, but probably shorter than that. I mean, intra-seasonal variability within the season. And the mesonet, I could try everything together, is designed more to deal with the actual weather systems that are taking place. So we're talking about hours and days. So there's a cascade of, they're all interacting with each other, which complicates things. But in terms of forecasting, they tend to sit in these different overlapping times. So I think I've tried to integrate those three things. And in the background is always the slow trend in terms of climate change. So there's a mixture of different timescales with all those things.
I think climate science is becoming more and more specialized over time. We have experts in El Nino, experts in the polar stratosphere, experts in many other areas, but most of the changes, I think in the future that will yield the greatest improvements in our understanding of the system as a whole involve people who work across these different phenomena. We may understand really well how one or the other behave, but these things interact with each other in ways that we really don't understand well. And I think that that's a big open area for learning in the future.
And I'll just add, there's that idea that interaction needs to happen is a motivation for a lot of different projects that are currently ongoing. There's organizations that are looking at this sub-seasonal time scale that have people who are have expertise in looking at El Nino and oscillations that occur in the tropical regions. People who are experts in stratospheric dynamics, and bringing all these people together to force them to have conversations, to look at the interactions. So there's definitely work going on to get all these people together in the same room to have the common motivation of improving our forecast models. So that's something that's currently going on and currently a hot research area.
I think we have time for one more question.
Okay. Yeah, I'm sorry, I know the emphasis is more on natural variation, but I still have a climate change question. With the change in the, I wonder whether there's a change in the wind patterns. We have a change in the gaseous composition of the atmosphere. We have more particles in the atmosphere. And because of warming, we have more moisture in the atmosphere. And I wonder, how does that affect wind patterns, wind velocity, patterns of wind? Would that be changing the kind of friction between the atmosphere and the spinning of the Earth? I mean, what are the effects, not so much just on the warming, but actually on the patterns and the velocity of wind on Earth? Thank you.
Well, I was going to say, just in terms of, since I was talking about the winds and associate it with the large-scale circulation in the northern hemisphere, there have been efforts to understand how the strength of the vortex will evolve in a changing climate situation. And what they've basically the research is currently showing is that you get more, as we have a warming planet, the jets will shift poleward, which means that you'll get more interaction from wavy structures that may be forced by El Nino conditions, but those waves are the triggers for the weak stratospheric vortex, which means that we're more likely to have weak vortex conditions in the winter as we move forward in a changing climate. So that's the very large scale during the winter season, but there's also changes in the surface winds in the equatorial Pacific regions and elsewhere.
It's a really good question. That was a great answer as well. So, but I wanted to highlight, in terms of an educational point of view, in my talk I show global average temperatures, and there's a lot of certainty about how that's changing. The next level down would be to look at more global circulation patterns, and Andrea is talking about that. So there's some certainty about that. As you go into smaller regions, there's less certainty, but there are some regions which are more certain than others. High latitudes, there are changes in the shifts of overturning circulations in the tropics. And then you go down into local regions, and that's where uncertainty becomes even higher. So there certainly are expected changes in the circulations. So we're more certain about the large-scale changes and less certain about the local changes. So I don't know if that answers it. But certainly, we haven't given emphasis to that, but it is emphasized.
You want to try one more? Okay.
Just very quickly, and I'm sure this is something Paul can relate to, something we see in the news a lot. If anyone would care to comment how this impacts the drought conditions that we've been seeing, particularly in the Southwest and even up here. So how this might affect the drought. Thank you.
This is another complicated problem. The California drought has developed in association with varying patterns over each of the years in which it occurred. So it wasn't like some single consistent cause, but extended year over year, several events that happen to line up together have generated that pattern. And it may be exacerbated by climate change in terms of increasing the temperature of the Earth's surface in California. But several papers have illustrated that internal atmospheric variability and interaction with the ocean may be responsible for much of those signals. And that kind of event has occurred naturally in the past. So we may get worse into the future, but that's a difficult question to really pin down firmly.
Okay. Thank you. At this time, we're going to do a switch here to our second panel of three. So I want to thank everyone who had a question and our three panelists for the first part of the presentation. And we're going to do a swap here to our next three panelists, Everett Joseph, Raymond O'Keefe, and David Valley.